We present a new approach for rigidity analysis and structural reinforcement of mechanical assemblies. In this example, our method computes the external loads that maximally deform the assembly. Based on the analysis, our system guides the user to enhance the rigidity by introducing new parts to the assembly. Before showing more examples, we briefly explain our worst-case rigidity analysis. Our method for rigidity analysis is based on the analysis of eigenvalue and eigenvector. For the simple assembly on the left, we show how elastic potential energy changes with the node displacement on the right. We find the worst-case load for the assembly by finding the direction of the smallest second-order derivative from the origin. Our method automatically finds the direction by finding the eigenvector associated with the minimum eigenvalue, see the red arrow on the right. This is a moving direction that does not induce elastic energy, meaning the assembly is flexible, while the eigenvector associated with the minimum non-zero eigenvalue indicates the external loads that maximally deform the assembly. Based on our rigidity analysis, our method can aid the users to improve their structural rigidity of their assemblies. Our rigidity analysis is differentiable with respect to the geometric parameter of the input assembly. We develop a gradient-based method for optimizing the assembly's geometry, where we employ gradient descent to iteratively update the node's position to improve the worst-case rigidity. Based on the worst-case external loads, our method can reinforce the assembly by suggesting additional supporting parts. Where our method generates a set of candidate parts that connect different parts, and select the candidates of the longest projected red line as the final suggestion to the user. Here we incrementally reinforce an assembly and show the according increase in the rigidity value. We validate our approach for various assemblies and use our method to guide the design of mechanical assemblies. To demonstrate the effectiveness of the continuous rigidity optimization, we run our algorithm on a reinforced planar boomerang silhouette. Under the same external load, the optimized reinforcement reduces the deformation of the silhouette. We also apply the computation on a multi-piece bunny silhouette. With topologically identical reinforcement, we optimize the length of bars to enhance global rigidity. According to our physical experiment, the optimized bunny offers higher stiffness with the same payload. Besides the rigidity optimization on continuous configurations, our system can also guide the user on adding distinct reinforcements. In this example, the input sliding handle model has 1 degree of freedom in the direction shown with green arrows on the left. Our system searched for all the possible reinforcements and found the most durable fixation shown on the right. We designed several rigid mechanical assemblies as guided by our method. In this example, the wing of the Bernd model is easy to deform. According to the worst-case external loads provided by our method, we can add a horizontal beam to reinforce the assembly. The drying rack by default fails under the torsional motion, while by adding reinforcing rods suggested by our method, we make the rack more stable under the same external load. Finally, we found our system also benefits the prototyping process in industrial design. For example, the boat model was built without stability into account. Our method enhanced the model by adding 2 rods. The simple changes strengthen the model towards the floating force along the 2 ends of the boat. Thank you for your watching.